opportunity to present our really preliminary result on some eruptive stars. Well, we are working for these outbursts, and of course the first step, we need to discover them. There were already several proposals for that. Well, our technique changed. On the left-hand side, you see the late Albert Jones, maybe the most famous amateur astronomer, who discovered two large eruptions of EX Lupi 50 years, maybe with the same instrument even, I don't know. The right-hand side, what you see, that is a much more modern discovery machine. In this case, this is from the Gaia survey. So you have really a kind of, and you select from the large data set automatically. I mentioned Gaia, not accidentally. I want to advertise a little more. It could be really a for us to discover the new lightnings. Here, that is a kind of summary of Gaia surveys, including some important things like the average cadence, the leading magnitude, and the fraction of the sky covered. So I would like to emphasize that Gaia is one of the sky surveys, what it does. Actually, this is the mission of the it runs from 2013 until the present, and has more or less a monthly cadence. So we, for the last 10 years, actually, we have for the whole sky an observation every month for 1.7 billion stars. So that's really a good starting database. And there is an interesting service for Gaia, alert detecting machinery, where our group is also involved a little bit. And we detected and published 26,000 alerts. Interesting. These are not all young stars. The number of young stars is much lower. Before Lynn asking how to identify young stars, actually there are, basically we use catalogs from the literature to compare with. So Gaia is really a nice machinery to publish new interesting events, and we study them. This is a summary of our group. We basically check every morning the new alerts to see which could be young stars, and with those where we find interesting, our weekly meeting we discuss and we publications. Basically, we perform photometric and spectroscopic follow-ups, and based on this, with some modeling, we publish them. I think it's already a quite nice, and it's still increasing. Our follow-up data are mainly for shooter specs and for infrared photometry. So that's interesting, and this we do every day. But it means that we have more and more interesting young sources from the Gaia system. So maybe it would be interesting to see if we can use them for some statistics already, because that's growing. So for that, last year at the Protostars and Plus meeting in Japan, I saw this interesting figure. It was from the accretion chapter, the chapter 10. It is an attempt actually to distribute somehow and to differentiate the location of variable young stars on a parameter space where one axis is length, the time scale of the event, and the axis is the amplitude. So you see that our the EX Lupi outbursts, F-Uranus outbursts are all here mentioned. So I just wondered if in the next step we remove all these unimportant and uninteresting things which are related to fading or by only the accretion events we are after in this conference. So the question whether real events follow this scheme which was presented at the Protostars. So how could we check? Maybe we can check this distribution using Gaia, the Gaia alerts. So why could they be a good database for that? Because we have a long, data sequence. There are plenty. They are kind of unbiased. I mean, they observe the whole sky, but since I know how they say, I would not say it's an unbiased sample at the moment. And for free, you just download them from the survey. So let's see. We could use the Gaia alerts would distribute on this the right way by the authors of the chapter. For that, of course, you need to look at Gaia alerts. We have about 10,000 about 1,000 cases which we think young stellar objects. And then you need a student who will put them one by one, like this. At least one student, a patient, who will take the mouse and click at the right place, more or less, and just with a visual inspection, try to determine which are the accretion events. It's really not easy. It's not easy to differentiate extinction events in many cases, surprising many cases. But I had a good student. So finally, from 283 YSOs, which is only about 5% of all Gaia alerts, in about 30%, we found something which we said, it's an accretion event. It's good for the moment. And actually, it's about, so it's, most stars showed not only 1, sometimes 2, like here. In average, we have 1.5 event per source. Of course, there is a kind of mission parameters that with the monthly cadence cannot get much very short events, and with the 5-year or 10-year running, you cannot get a century-long F-Uranus outburst, of course. Let's try to distribute this, because we measure the length and the amplitude of them on this plot. They distribute like this. What do we see? First of all, they are more or less at the right place. I think that's good, and to the authors of the protostars and planet chapter. Distribute from the very small kind of normal variability until Uranus events. From left and right, as I mentioned, because of Gaia, we cannot get magic. I think, though, in that chapter, note that the normal variability is considered more than 1 magnitude. And they call bursts 2.5 magnitude. And I tied kind of seeds which correspond to things, maybe a division line, there are a lot of points. And that is another group which are just kind of burst. Everything we heard that and maybe longer, that's called outburst in the chapter. And I think we these lines and 1 and 2.5 magnitude are drawn at the kind of good right places. There are some points I need to discuss with Lynn and Agnes, who are the authors of this chapter here. So what points which should not be here? What are these? They belong to any blue squares before, but addressing the details. Okay. In the plot originally, there was also a protostellar outburst infrared. Because with Gaia, we cannot get these guys. So just to make this study complete, and since I had still the student, that's why we saw that we would check the NRAO light curves with the same way, with the same mouse clicking on actually, or the light curve. We are about more than 10 years curve, but with half-year sampling. So we try to pick up this kind of events. These are Weiss light curves, so we are at 3 and 4 micrometer what we are studying. Again, we had some 700 objects. Here, it's important. We did not take Weiss light curves of the cycles. We had this is 1 objects. So this is for the every young star. Here we took only a class 1 objects. And from that, about 30%, the same ratio as for the Gaia source with some eruptive events. And again, we have a database of accretion events in the infrared. how they are distributed. Blacks are the Gaia sample, which I showed before, and the red ones are the new ones. Here, to my surprise, actually, most of the variations, so most of the events, what we judge event, they are really small. Maybe this maybe this is just some kind of really normal variability. But there are others in the infrared, mid-infrared amplitude. In the infrared. That's the infrared, that's at the YEMS magnitude. As I mentioned, individual events. Follow-up mainly means a spectroscopic follow-up with light spectrum. And as you know, in many cases, what you see that you may see an absorption-like spectrum, which is a kind of F-Uranus type spectrum with a CO absorption and all lines in it. Or you may see something which is more emission type, so a lot of lines. So just a very quick and dirty, we collected spectroscopic information either from our unpublished spectra or from the literature for the Gaia alerts, which are shown. We don't have for too many, but some 40, 45 objects we have could classify just in a quick and dirty way if it's emission or absorption or emission plus absorption, because there are also cases like this. And we just wanted to check how they are distributed in the same way. So, which are absorption spectrum, classical F-Uranus type spectrum, they are big red dots. And the emission spectrum, which is the EX Lupi type thing, they are the green or the yellow. First, I saw that this is just a chaos, and I did not see much discrepancy by deviation. But actually, the red ones, this kind of Fjord type spectra, occupy this part of the of the parameter space, where really fjords, exors, and protostellar outbursts are located. And as if there would be a line here, so the emission line objects are many below that. And here we don't see absorption-like spectra, only at longer time. So maybe there is some structure within that figure, and certainly we would need more data to see how they are distributed. I simply wanted to see an overlapping region where we may have for the same kind of burst either absorption or emission spectra. And I think we do in this part for the same outburst parameters, we may have spectra. So probably different type of physics can produce the same kind of amplitude. How much time do I have still? Oh, perfect. So there is one point I did not mention in the original, the first what we saw, that it's not only that which part of the parameter space is occupied, but how often it's occupied. So with other words, we can actually check the surface density of these points on this figure. If the original data set was an unbiased sample, then from the surface density of different parts of this parameter, we can check what is the relative incidence of the large outbursts or the small bursts, how many times more small bursts or small bursts you have than the very F-Uranus type outburst. So I think that will be an interesting question, but we cannot answer at the moment this Gaia alerts thing. This is not an unbiased survey. But later, have the Gaia DR4. I'm really waiting. We will do this exercise and try to get a surface density map on this figure. Why could be interesting? I give just one example. If we check individual outbursts for our favorite stars, EX Lupi, we can check its effect on the interstellar disk. For example, in 2008, this star showed a big outburst discovered by Jones, and we discovered that a large amount of crystalline silicates were produced during the burst. Simply, was the inner part. Even we could quantify, so we have a number how these stars were produced in the burst. Interestingly, last 2 years ago already, there was another outburst of the same star. It was much smaller. It was studied by my colleague Fernando, who's could comment on that, sitting here. So that was a smaller outburst, or we called it medium burst. And we also want to see whether there is crystal formation in a smaller burst. Well, it is still, we are visiting. There are some metric 10 micron data which seems to show some crystal signatures, but we also observe web halfway after this intermediate outburst that we didn't see any crystals. So we still don't know. But the main point that if we could check individual objects and their effect on the disk in any way, crystallinity, changing the chemistry, changing the structure, ionization, any kind of parameter you can imagine, then we study individual objects. How much such a big outburst would modify the disk? How much such an intermediate outburst would modify the disk, which is the planet formation place? How much such a smaller brightening would modify the disk in a certain sense? Then, if you have these individual studies, then you need to multiply it by the surface density, the relative number of this outburst, to evaluate the total cumulative impact of the eruptive on the disk. So that small and how many large bursts you have, and then multiply it in a sense with the result of the individual study. So, as I mentioned, it's a preliminary study. It's not only because we're lazy to evaluate the light curve shape of or and so on. The student, of course, had others. But we are waiting for the Gaia DR4, which would have a kind of unbiased things. It will be published in early 2026. And after that, we can do this amplitude event length plot in a really professional way. What we know this kind of pilot study. In DR4, we will have 3 bands also. The G band, the Gaia D band. Then we have 3 colors, so we can differentiate better against the extinction effects. That will be a big step. When Gaia DR4 is out, we will need to write a software and try to automatically find all the eruptive events in this 5-year sky. We will do that. And of course, the events will be in the 3 months to 5-year time scale. I hope that we will have a relative bias in database of eruptive events of the last 5 years. And then this kind of analysis, what we do here, we can use and do with the DR4 data. And the DR4 will be an unbiased survey of the whole sky, including all young stars what are observable with Gaia. I can also ask whether all young stars go through this kind of events, which fraction of them do that. Many thanks for the attention. So please wait for DR4.
We have time for 1 or 2 questions. Yes.
Hi. Can you go to the plot where you show the amplitude of the objects where you have spectroscopy? Yeah, this one. So is this amplitude the Gaia amplitude for all of these objects?
This is the Gaia amplitude, exactly.
So you have a few objects with like 1 magnitude outburst and showing absorption spectrum?
Only these 2. Well, you have to term light curve which goes through decades. Then during the 5 years or 10 years Gaia time, you may have a detect much amplitude because it does not include the whole history.
Okay, so you haven't
you
seen
take
the
an
outburst.
amplitude which is within the Gaia observing
okay.
sequence, leading.
Okay, so just you haven't seen the outburst in these objects.
Maybe we checked, but now we did it just automatically for objects. So with individual investigations, may turns out what the real quiescent phase.
Okay.
One more question over here.
So all this, thank you for the talk. All this was observational. So do you have a theory behind that plot? I mean, is it like 1 over F noise, or what is the idea?
I asked the authors of the chapter, I took the chapter.
What is the possible idea behind observations in terms of theory?
That the question is basically, why don't we have very short time scale, very high amplitude variations here? I think that's it. Well, I don't know. That's it.
Let's thank Peter once again. Also thanks all the speakers from this morning. We'll take a short coffee break now. We'll be at 11:15. And a kind reminder to please not to bring any food to the auditorium.